students, welcome to this session. So now we will move on to Unit 2 of the topic Safe Water. So in the previous session, I have already told you the objectives of this topic. So this is Unit 2, Purification of Water, covering CBME Competency 3.2, and these are the learning objectives. That is, we will discuss purification of water on a large scale and on a small scale. So purification of water needs to be done to provide safe and wholesome water, and it can be done on a large scale to provide a whole community or habitation, and on a small scale also for domestic consumption of water. So let us first discuss purification of water on a large scale. So the components of purification are storage, filtration and disinfection. These are done in stages to get pure and wholesome water. Okay, so we come to storage. Storage has a very important purpose, that is, when water is stored for a long time, there is a lot of natural purification process going on. So by this, the physical quality of the water gets much better. 90% of the suspended impurities, they settle down as sediments and the water becomes clear just in a day. Then there is chemical purification occurring. So there is dissolved oxygen in the water, which I had told you in the earlier session. So this dissolved oxygen is utilized by aerobic bacteria present in water to oxidize the organic matter in the water. So therefore there is a decrease of free ammonia and ammoniacal nitrate, and the free nitrate increases. And there is also simultaneously biological purification, that is, the organisms present there, virus, bacteria, etc., they all die out gradually, and by a week it drops down to by about 90%. Next is filtration. So filtration again brings down the bacteria count by another considerable quantity, and so it comes down to 98 to 99% purification. So filtration can be done by two ways. One is rapid or biological sand filter, and another is mechanical or rapid sand filter. So next stage is filtration. So filtration removes 98 to 99% of bacteria, and this can be done by two processes, either biological or slow sand filtration or mechanical or rapid sand filtration. So biological or slow sand filter. So these are the elements of a slow sand filter. First is supernatant or raw water, then bed of graded sand and gravel, then an underground drainage system, and finally control valves. I'll discuss each one by one. So this is the diagram, a slow sand filter. These are the parts and this is how it looks like. So now let us discuss the parts of slow sand filter one by one. So on top there is the supernatant water. So this is up to a depth of about 1 to 1.5 meter, and such a huge volume of water, it creates a pressure which helps the water to trickle down through the sand that is placed below the water or on the filter bed. And along with that, the volume of water that has a waiting period of 3 to 12 hours again undergoes purification by sedimentation, oxidation, etc. Next, below this is the sand and gravel bed. This is of a depth of 30 to 40 centimeter, and it contains layer after layer, fine sand, fine gravel and coarse gravel. And this should be free from clay and other material, because this is where the filtration will actually happen. So if this is dirty, then the water will get dirty. So it should be taken care that it is cleaned regularly. So water here undergoes purification by mechanical straining, that is when it passes through the sand, gravel, etc. Then sedimentation happens, absorption of the impurities on the sand particle happens, and simultaneously oxidation also happens. So with prolonged use, gradually a layer is built on top of the sand bed, that is the vital layer. So what is a vital layer? It is a slimy layer on top of the sand bed of about 2 to 3 centimeters thickness, and it consists of algae and other forms of life like plankton, diatom, bacteria, etc. So these collect as the water trickles down, or as the water is staying there on top of the gravel bed, sand bed. So these algae and bacteria, etc., they settle down on that and gradually they thicken and the layer forms. So this layer is very important. As it is named vital layer, it is very vital for purification in this process. So it is said to be the heart of the biological filter. Why? Because it removes the organic material and bacteria there present in the water, and it oxidizes the ammoniacal nitrogen into nitrates, and thus the purification happens. So in this slow sand filter, purification happens in two ways. One is a mechanical strainer when it passes through the sand and gravel, and secondly also biological process through this vital layer. So beneath the sand and gravel bed, there is the system of under drainage pipes which carry the water from the filter outside. So this consists of porous or perforated pipes. So the water that trickles down the sand and gravel bed enters this tubing system through the pores or perforations, and they are carried outside. So along with providing as an outlet for the filtered water, these porous tubes also serve as a support for the gravel and sand bed above it. So beneath the sand and gravel bed, there is a under drainage system. It consists of pipes which are porous or perforated. So the water that trickles down the sand and gravel bed enters these tubes through these pores and perforations, and they are carried outside. So these tubes provide outlet for filtered water, as well as the pipes support the filter mechanism above. So the sand and gravel bed that is there, so it is supported by these pipes below, and all these are contained in a filter box. So in the control system, there is another device, the Venturi meter, which measures the bed resistance. And this bed resistance is the resistance that is offered by the sand and gravel bed to the water that trickles down it. So when this resistance increases, the filter functioning becomes poor, and so cleaning has to be done at that time. So the filter box, as I said, it consists of a rectangular open box which is made of concrete or brick or cement or stone, and it may be partially above the ground and the rest of it below, or it may be totally underground. So these are the parts in it: the supernatant water 1.5 meter, then the Zuglial layer 2 to 3 centimeter, Zuglial layer or the vital layer, then sand bed 1.2 meter, then gravel support 0.3 meter, filter bottom 0.16 meter. So next is mechanical or rapid sand filter. So there are various processes which are performed in this system. So this is the rapid sand filter. So first of all, coagulation is done. So the raw water is mixed with chemical coagulant, that is alum, and rapid mixing is done in a mixing chamber for a few minutes. Subsequently, it is stirred violently, vigorously in a flocculation chamber for about 30 minutes, and it is left thereafter when the flocculant precipitate settles down at the bottom. So these are containing the impurities and bacteria, and which have formed floccules along with the alum. And next stage is filtration, that is the partly purified water passes through the rapid sand filter. So the parts of a rapid sand filter are similar to a slow sand filter, that is there is a supernatant water, then there is a sand bed, there is graded gravel, there is under drainage system with control valves, same as the previous one. So here, like there was a vital layer or Zuglial layer I told you in the slow sand filter, here there is a alum flock layer. So what happens is the alum, the coagulant, it reacts with the impurities and bacteria in the water, and it forms floccules as we discussed in the previous slide, and these get deposited on the sand bed and it forms a slimy layer like the zooglial layer, and this absorbs the bacteria from the water, and this also affects purification. So now let us come to cleaning of sand filters. They need to be cleaned regularly. So how are they cleaned? So slow sand filter is cleaned by scraping, and it needs to be done monthly. And so when the resistance is lost, as I discussed in the previous slide, then scraping is done. The top layer of the sand along with the vital layer is scraped off. So around 1.2 centimeter of sand along with the vital layer is scraped off, and then the filter is made to function again. Again, it takes a few days to form the new vital layer. Rapid sand filter is cleaned by backwashing. So that is reverse flow is done. The water is flowed from the bottom to in a reverse direction, and this needs daily or weekly cleaning. But it is comparatively easier because it just needs to change the direction of the flow and it happens automatically. So advantages of filters. Slow sand filter is simple to construct, operate, it is cheap, and it requires less frequent cleaning, monthly as I said. And quality of water provided is quite high. Rapid sand filter, on the other hand, can deal with raw water. So in slow sand filter, there is initial storage for a long time. Here that is not required. It is mixed with alum, and within a short time it can be passed through the filter. No preliminary storage is needed, and it occupies less space. It is smaller in size and it is very rapid. Much faster it operates than a slow sand filter. And washing is easy as I told you, but it needs regular cleaning, daily or weekly, and it is flexible in operation. Next, after filtration is disinfection of water. So disinfection is done by chlorination, ozonation, and further filtration can be done at the consumer level. So let us talk about chlorination first. It is a very important and very effective method of disinfection. So principles of chlorination. So chlorine in the water, these two react to form the hypochlorous acid and hypochlorite ion. These are the reaction steps. So water plus chlorine gives hydrochloric acid plus hypochlorous acid. Hypochlorous acid, some of it breaks down into hypochlorite ions and the rest remains as hypochlorous acid. So both are very good strong oxidizing agents, but hypochlorous acid is more effective than hypochlorite ion. And at higher pH, the hypochlorous acid tends to get converted into hypochlorite ion. So functioning is better at lower pH because more concentration of hypochlorous acid is present in the water. So what needs to be done? The water should be clear and free from turbidity. The chlorine demand needs to be estimated. Contact period of 1 hour to be maintained, and residual chlorine of 0.5 milligram per liter after 1 hour should be present, and hence the correct dose of chlorine is the chlorine demand plus residual chlorine of 0.5 milligram per liter. I will explain these terminologies. So this you have to know very precisely, and you have to remember the amount of concentration of residual chlorine and the contact period. So these are very important for MCQs, Vivas and everything. And the terminologies that I will discuss now, these are also very important. These are important again for MCQs, these are important for Viva and can also come as a short note, etc. So what is residual chlorine? Residual chlorine is the amount of free chlorine present in the water after a contact period of 1 hour, or it is the extra chlorine that appears in the water after all the organic and inorganic matter has been oxidized. So this is required. Why do we need to have residual chlorine? We have already done the disinfection, but this amount of residual chlorine takes care of further contamination. If the stored water subsequently gets contaminated, this residual chlorine will help to disinfect that. So that is why it is required at a concentration of 0.0 milligram per liter. Another term is breakpoint chlorination. What is this? So this is the point at which all the organic inorganic material has been oxidized and residual chlorine just starts appearing. And the third term is chlorine demand. So chlorine demand is the amount of chlorine required to oxidize all matter in it, that is inorganic and non-organic matter, and destroy all the bacteria, all the impurities, everything. So whatever chlorine amount is required, that is the chlorine demand. And this is calculated as the amount of chlorine initially added to the water minus the amount of chlorine that is remaining at the end of 1 hour, that is the residual chlorine. So this, after subtraction, the amount that remains is the chlorine demand. It means that amount of chlorine was utilized for oxidizing the impurities, bacteria, etc. that was present in the water. Chlorine demand is measured by the Horrocks apparatus because this is required because water is of different quality at different places. So there cannot be any standard thing, that amount that this will disinfect all types of water. If our water is very contaminated, that will require more amount of chlorine. And if it is a comparatively pure water, that will require less amount of chlorine. So how do we estimate that amount of chlorine? So it is done by the Horrocks apparatus. This is the diagram. This is the schematic diagram of the Horrocks apparatus. So the purpose is to estimate the dose of bleaching powder that will be required to disinfect any sample of water. Like we want to disinfect water of a well. So we will take a sample of that well water and then we will estimate the amount of chlorine required and that bleaching powder required. That amount of bleaching powder we will use to disinfect the well. So it contains 6 white cups you see here. Then there are, each are of 200 milliliter capacity. Then there is one black cup. There is a metal spoon. The spoon holds 2 grams of bleaching powder. Then 7 glass stirring rods, a special pipette, 2 droppers, indicator solution and instruction manual. So I'll tell you the procedure, what to do and how to do it. So the procedure of testing the water, estimating the amount of chlorine or bleaching powder to be required to disinfect. So first we have to make a stock solution with 2 grams of bleaching powder, means 1 spoonful of bleaching powder, the spoon that was provided in this Horrocks apparatus. So we fill that up to the brim and add a little bit of water and make a thin paste and then add more water and stir with one stirrer to make a solution. This is the stock solution. And we allow it to settle so that some sediments may fall down. Then we fill the white cups with water that needs to be tested. So up to a level of 1 centimeter below the rim, we fill all the white cups. Then we take the stock solution with the pipette and we add drops of that stock solution to the different cups, all 6 cups. And how much do we do? We add 1 drop to the first cup, 2 drops to the second cup, 3 drops to the third cup, so on and so forth until we have reached the 6th cup where we put 6 drops. And then we stir each cup. We use a separate pipette. There were 7 glass rods. So we use a separate glass rod for a separate cup to avoid any contamination from one from the other. Then we let them settle for 30 minutes. After that, we add 3 drops of the indicator solution to each cup and stir again. And then the first cup that shows blue color indicates the amount of bleaching powder needed. That means the number of spoons that are needed. See, if the second cup shows blue color, that means we need 2 spoonfuls of bleaching powder. And that means number of spoons into 2 grams, because you remember 1 spoon is equal to 2 grams. So that we calculate is equal to so and so gram, and that amount of bleaching powder will be required to disinfect 455 liters of water. So this is the standard procedure that can be followed. So the forms of chlorine that can be used for chlorination. We can use chlorine gas. Remember this, we were talking about purification on a large scale. So chlorine gas can be used, which is the gaseous form of chlorine, but it is very irritant to the eyes and it needs a special equipment, instrument, chloronome, to apply the gas. So this is not very feasible. Then there is chloramine, which is a compound of chlorine and ammonia. Or there is perchlorone, which is a combination of chlorine and calcium. So these can be used. They provide more persistent residual chlorine and less chlorinous taste, so more palatable, but they are slow in action, yet they are good. Then there are other methods, that is ozonation can be done. That is, ozone is another powerful oxidizing agent and it can oxidize organic and ammoniacal substances, and it does not provide any taste or color to the water. So that's why it makes it acceptable. But it has no residual germicidal effect and it is quite expensive. So ultimately it is not very feasible. Then there is process of filtration that can be done by various techniques, reverse osmosis, ultrafiltration, nanofiltration, microfiltration, etc. And they are very effective in removing all impurities and killing bacteria. So with this, we come to the end of the purification process for large scale provision of water. So now we will discuss purification of water on a small scale. Actually, what needs to be done at the domestic level, so that when you give health education to the families that you visit or to the patients or other people that you educate, so you can tell them about all these different kinds of ways of purification at the household level. So these are the ways: boiling, chemical disinfection, filtration, ultraviolet radiation and reverse osmosis. So we will discuss each. So boiling is a very good method. It is the best method in fact. So what needs to be done is first boil the water, bring it to a rolling boil. That means when the gases dissolved in it come out like bubbles. So that rolling boil state has to be maintained for 10 to 20 minutes. This is required for killing all microbes in the water. And after that, water becomes sterilized. Very good quality water, and it even kills the spores, cysts, ova, etc. And it also removes temporary hardness. But the problem is that fuel is very expensive, so it cannot be afforded by everyone. And moreover, there is no residual action in it. Next method is chemical disinfection. So chlorine is the most commonly used one, and it can be used in various forms as bleaching powder, chlorine solution, chlorine tablets, high test hypochlorite, etc. So any of these methods can be used, and other than that, other chemicals may be used are iodine and potassium permanganate. But these problems are potassium permanganate colors the water, and which may not be acceptable. And iodine also provides a taste and smell to it and a color to it. But more important problem of iodine is it is biologically active and the thyroid glands may be affected. So this is not a desirable disinfection method. Next is filtration. So this is a quite popular method and quite affordable, cheap method. There are ceramic filters which are available. So different types of ceramic filters, and they have a candle, they have a container, two containers, one above the other. The upper container holds the water that needs to be disinfected, and the lower container collects the disinfected with the filtered water, and it can be collected by means of tap for consumption. So the upper container contains a candle through which the water passes and gets filtered. This candle gets dirty obviously because the impurities are deposited on it, and hence it needs to be cleaned very regularly. Other methods are ultraviolet radiation. So a film of water is exposed to mercury vapor arc lamps, and thereby this ultraviolet rays that the water is exposed to cleans the water of all impurities, including turbidity, bacteria, microbes, other microbes, etc. But it is very costly, and again it has no residual action. Then there is the multi-stage reverse osmosis, which is quite common nowadays. RO it is known as colloquially. So this demineralizes or deionizes the water. So it removes the minerals, it removes the other particles, it removes the microbes, etc. And why is it known as reverse osmosis? Because the process of osmosis is reversed in this system. So osmosis, generally what happens, from the lower concentration side of the membrane, the water goes to the higher concentration side to balance the equilibrium on both sides of the membrane. But in this case, what happens? The water that is of higher concentration, that means water, raw water that contains minerals and other impurities, From that, we need to draw out clear water that is of low concentration. So that means the process of osmosis is reversed, and this is done by passing the water under high pressure so that it crosses the membrane, osmotic membrane, and goes to the other side. The clear water and the impurities are held back on the other side of the membrane. And it kills all microorganisms. It is very effective, but again, it is a very costly method and it has no residual effect. Another way of treatment of water that is required is removal of hardness of water. So what is hardness of water? We always talk of saying that this is hard water, this is soft water. So what does that mean actually? Hardness is when there are salts present in the water, and water that has no salts present is soft water. So hardness can be of two types, temporary and permanent hardness. Temporary hardness is caused by bicarbonates of calcium and magnesium, and permanent hardness is caused by sulfates, chlorides and nitrates of calcium and magnesium. So method of removal of hardness, these are the ways by which temporary hardness can be removed, that is by boiling. I already said in the previous slide that boiling removes temporary hardness. Addition of lime removes temporary hardness. It can also be removed by addition of sodium carbonate and by permutate or base exchange process. On the other hand, permanent hardness can be removed by addition of sodium bicarbonate and permutate or base exchange process. So that means boiling and addition of lime does not remove permanent hardness. It only is capable of removing temporary hardness. So with this, we come to the end of this session. Let us sum up what was discussed here. We discussed purification of water on large scale. There we discussed slow sand filter, rapid sand filter, slow sand or biological filter, rapid sand or mechanical filter. Then we discussed the steps, that is storage, disinfection, storage, filtration and disinfection. Then we discussed the principles of chlorination. We discussed the terminologies, that is breakpoint chlorination, chlorine demand, etc. Then we also discussed Horrocks apparatus, that is the apparatus or equipment to measure, to estimate the amount of chlorine required to disinfect water. Subsequently, we discussed purification of water on a small scale or at the consumption domestic level. So there we discussed the various methods: boiling, chemical disinfection, ultraviolet radiation and reverse osmosis. So again, I have given some questions here with the answer keys in the end for you to check your progress. So much for today, this session. I hope you have enjoyed the session and I hope you have understood it. Thank you.